All right, welcome to lecture 14, part 1. This is a relatively short lecture about equivalence relations. So we're going to review partitions of sets and define what is equivalent relation based on partitions of sets, and then give a review of property of relations and talk about equivalent relation via those properties. And finally, we'll give one example of how to prove for equivalence relations. All right, so first of all, let's review partition of sets. If you have a set A, a partition of set A is a set of sets S, which partition the set into, say, n sets, such that each of the subset is non-empty. And for any two pairs, if they don't equal to each other, they have empty intersection. And finally, if I take union of those set, they are equal to the set itself. So it is really a partition in the sense that for the last bit, where an element in A is at least in one of those sets. Okay, so this is a partition of sets. Now, if we study equivalence relation, is if I have a set A and a relation R on A, in this case, R is a subset of A cross A. R is an equivalence relation on A if there is a partition of A such that whenever X, Y is in the relation, if and only if X and Y are in the same partition or same part of S. So in other words, that S is referred to as a partition of A induced by the relation. This will become more clear when you see an example. So if I have the set of numbers, hypothetically, let's say my set of numbers is 1, 2, 3, 4, and so on and so forth. And I define the equivalence relation when, for example, when A over B is equal to C over D, they are in the same set. When the second kind of equivalence relation you can define on is if you have a set of triangles, two triangles is equivalent if they are similar to each other, and you can define what is a notion of similarity. And then if you have a set of people, you can define two people are equivalent to each other if they have the same birthday. Okay, so there's various ways to define equivalence relations. Let's give a more specific example where we're going to check the properties. Remember, when we have the rule of set partition goes here, is that number one, each of those subset set is non-empty. Number two, for all pair, their intersection is empty. And the third one is a union of all those is equal to the original set. Those are some of those rules of set partitions. So now the set itself contains 6 elements, 1, 2, 3, 4, 5, 6. And we define R to be 2 elements is in the relation if their difference is even. Okay, so now what we're going to do is look at the partition of the set A based on this relation, which gives me the partition of the set A. Why is that? Because if I'm looking at the element 1, 2, 3, 4, 5, 6, you know, one way to think about it is through the arrow diagram. 2 element is part of the relation R if their difference is even. So 1 minus 3 is even, so they're in this relation. 1 and 2, the difference is odd, so they're not in the relation. Similarly, 3 and 5 is in the relation. 4 and 6 is in the relation. 2 and 6 is in a relation. What else? 1 and 5 of course, is in the relation because the difference is -4. And 1, 2, 3, and 2 and 6 is in the relation. All right. So now when we think about the partition, is you are looking at the separation of this based on treating this as equivalence relation. Hypothetically, you have, if you look at the arrow diagram, you're going to look at the connected components of this arrow diagram. So I'm going to highlight 1 and 3 are in the same set. 3 and 5 is in the same set. And 2, 4, and 6 in the same set. Since there's no arrow between the yellow element and the green element, they belong to separate connected components of this graph that form the partition. But of course, let's verify that this partition, this is S1, this is S2, satisfy the properties of set partition, the rules of set partition. Number one, neither of S1 and S2 is empty. Number two, those two set, S1, S2 has non-empty, as empty intersection. And three, the union of this two set is equal to A. So indeed, this is a partition. And therefore, it's also, by definition of equivalent relation, is also in equivalence relation. Okay, all the points, sorry, all the numbers in the first set is in the same, is defined by the equivalence relation. All the numbers in the second set is defined by equivalence relation. Okay, so now let's look at the property of relations. Recall from lecture 13, we are talking about various property of a relation. Number one is this reflexive, which means even only if A and A is in the relation R for any A in the set. Is it symmetric? If it is symmetric, if it is for or AB in the set, AB in R implies BA is in R. Last one is it transitive. Whenever AB is in R and BC is in R implies AC is in R. Okay. So a relation A on R on A is an equivalence relation if and only if it is reflexive, symmetric, and transitive. Okay. So for something to be equivalence relation, it has to satisfy those three properties. So one of the questions for you to keep in mind is that typically we can ask a following question. If a relation is reflexive, symmetric, and transitive, then R is an equivalence relation. And how can we prove this? One of those ideas is to use the definition of an equivalence relation with respect to the partition of the set. So let's go over our example. Let's say my A contains 6 elements from 0 to 5, and the relation is that AB has a relation, is part of a relation if their square differences is divisible by 3. Okay, so we want to prove it to be an equivalence relation, which means that we need to prove 3 things. Number one, we need to prove it is reflexive. Number two, we need to prove is symmetric. And number three, we need to prove that it's transitive. All right. Okay, so the easiest one is to show it is reflexive. What we do is we start with an element A that is in my set A. We want to show that the pair is in this relation. Okay. So what we can do, since A is already in the set A, we can compute A squared minus A squared, which is equal to 0, which means it's equal to 3 times 0. And then by the definition of the relation R, this means A and A is in R for all element A in capital A. Okay. Second one, in order to show R is symmetric, you are going to let a pair AB is already in the relation. Okay. It's already be given. Oh, sorry. Actually, let's start from beginning. If I want to show it's symmetric, what we want to do is we want to say I have a pair AB that is in the relation. We want to show B of A is in the relation. All right. So how do we do that? Let's say I have AB is an element in my set A, such that AB is in the relation. And then by definition of the relation, A squared minus B squared is 3 times M for some M that is an integer. If I multiply both sides by -1, what do we have is -1 times A squared minus B squared is equal to 3 minus 3 times M. Let's move on to the next page. This is still part 2. So now I have -1 times A squared minus B squared is equal to -3 times M. Do some rearrangement. I have B squared minus A squared equal to M of 3 times minus M. Because M is an integer, I have minus M is also integer. So B squared minus A squared is equal to 3P, where P is equal to minus M. Okay, of course, P is integer. So now you have B squared minus A squared is divisible by 3, which is part of the definition of R. Therefore, BA is also in the relation. Okay. So now let's look at, we want to show R is transitive. What we have is we say, I have 3 elements that is in my set, such that AB is in R and BC is in R. And we want to show that AC is also in this relation. Because AB is in R, and by the definition of the relation, we have A squared minus B squared is equal to 3M for some integer M. Because BC is already in R, we have B squared minus C squared is equal to 3K for some integer K. Now, if I add those two equations together, I actually get A squared minus B squared plus B squared minus C squared, which is equal to A squared minus C squared, which is equal to 3M plus 3K, which is equal to 3M plus K. Okay, so we have A squared minus C squared is equal to 3 times M plus K. And because of the closure property, M plus K is integer. So therefore, A and C is part of the relation as well. So that means, okay, so this is just a sketch of the proof. And I have typed in the actual proof in detail so that you're not missing many parts. So again, if we recall what is the proof techniques, to prove a relation is reflexive, you start with an element, any element in a set, and you want to show that A is part of the relation. If you want to show something is symmetric, you start with AB that is in R for any AB, and you want to show that BA is in R. To show it to be transitive, what you want to do is to show that whenever AB is in R and BC is in R, you want to show that AC is in R. Of course, for this particular problem, the claims to prove claim 3, the trick is to play with some algebraic manipulations to use the fact that AB is in R, so A squared minus B squared is 3M. and BC is in R, that B squared minus C squared is equal to 3K. And then through some algebraic manipulation, which is in this case, by adding those two equations together, you get a formula that is related to A squared minus C squared. Okay, so that is the highlight of this proof. All right, I will see you for lecture 14 and part 2. Have a good day.